Okay, so this talks about the A's distribution of politicians in a certain county is shown in the accompanying table. Suppose that a politician is selected at random. Okay, and that's going to be a key to answering some of these questions. We got to think a bit about this as we're going to pick one politician at random. Okay. So we're gonna select a politician at random and let A, B, and C be and S be these events. A, the event the politician is under 50. B, in his 50s, in his 60s or her 60s, and then event the politician is under 70. And then if we click here, we get the actual table. Okay, so we're going to use the table to find the probability of S. So the probability of S is the probability of this event that the politician is under 70. Politician's under 70, so that means, what does that mean? Could be in 60s, 50s are under, so that would be, these are all the possibilities that would apply to event S. Would you agree with that? Okay. So, so that probability is going to be the total number of possibilities for S. So this is would characterize S. So how many possibilities for S would be 79? 79 out of 99? Okay, so does someone have a calculator? It's going to require that I actually do this. So I'd guess is that 78%?
0.78. 798.
798?
Yeah.
It says round to 3. Okay, good job. So that was the easy one. So like 80% chance that if you pick someone at random, they'd be under 70. Okay, about an 80% chance. Okay, here. So now this is what I was talking about before. Express S in terms of the events A, B, and C. Okay, so we got to think about this. So you look at this and you say, under 50 is part of it. In his 50s, in his 60s. So this is really about events A, B, and C. But we're picking a politician at random. And so what we're asking is, if we're picking a politician at random, we're saying the event that the politician is is under 50 and in his 50s and in his 60s. Does that make sense? Mm-hmm. So you're picking one politician at random. Are we saying that that politician is under 50 and also in his 50s and also in his 60s? Or are we saying that politician is under 50 or in his 50s or in his 60s? Do you see that it's or? So yes, the S is the combination of those three sets, and so you might think and, but you have to keep in mind that we're picking one politician at random. And so we've got this one politician, now we're asking the question. If the politician is in set S, then that means they're either from set A, or they're from set B, or they're from set C. Does that make sense? So that's the difference between and or. You really have to focus on, you're going to pick one, and then you're going to apply these different categories to that one item. So that would have to be or. Because it's impossible for a person to be under 50 and also in their 50s and also in their 60s. So now, another question we have to answer here, is S, is it a probability? Is S itself a probability? No, it's just an event, right? It's just an event. So an event is not the same as a probability, so that would rule out A and C. Do you see that? So it's either got to be B or D. So we're forming a new event using the other letters. So it's not and, but or. because a person will be either in their 50s or their 60s or less than 50. They won't be all of those things. That would be and if they're all those things. Does that make sense? I'm guessing that was maybe a little bit of the confusion. It would be right, exactly, and we're going to talk more about that today. Okay, so the individual probabilities, I think, no problem, right? So it'd be 9 out of 99. Can you do those fast? So what's 9 over 99? 0.11. Okay, and then 32 over 99? 0.32 or 33 something. Was it? 323. Okay, great. Last one, 38. 384. Let's see how we did on those. Uh-oh. Oh, I didn't. Not enough decimal places in the first one. Thank you. Okay, good job. That's easy. So now, compute the probability of S using the special addition rule. Okay, and I'm gonna define that more specifically today. But if you're finding the probability of S, basically it's so the probability of S is then the probability of A or probability of B, probability of A or B or C. Okay, so then it'd be the same thing as adding those three probabilities together. And so you're going to get the exact same thing. So we should get the exact same 8.798 that we got before. So roughly or exactly equal to the same thing we got before. By looking at the sum of the probabilities of A and B and C, rather than grouping them all together and then dividing by 99. But it's the same probability, so you ought to get the same answer. That's the point. Okay, questions on this one? And this we're gonna do more of this kind of stuff today. Anybody have a question? Okay. Oh, I'm sorry. Uh-huh. All right, let me see if there was maybe one that. Okay. Oh, that's good. Not responding. Maybe can we try this? Maybe it's this. Maybe this one. 5.2.57, number 8. Maybe that has what you're talking about. What just happened? That's not what I wanted. Preview. Was it a dice one? Yes, this says not A. We'll try this one. So anyway, this side you had as a class there was a little more difficulty on this one. So let's try this. Hopefully it's one of the ones you're talking about. Okay, so we're gonna roll one die, and here's the events. The die comes up even. The die comes up 4 or more, and the die comes up at most 2. Okay, and so which outcomes constitute the event not A? Is this one of them? Okay, so what is A? A is the event the die comes up even. So so they're not asking for how many outcomes, but which particular outcomes are not A. So how about which outcomes are A? So which outcomes?
2, 4, 6.
She wants 2, 4, and 6. So what would be not A?
1, 3, 5.
Yeah, so 1, 3, and 5. So we're listing the outcomes that are in the set not A. Does that make sense? Okay, all right, A and B. Okay, so what constitute events A and B? So comes up even. So this is and now. So here's the key. We're gonna roll the dice once, and A and B both have to be satisfied. So even and 4 or more. So which events satisfy both those conditions? That's what we mean by and. 4 and 6. Again, and or goes back to, here's or. And or goes back to, you're gonna do one. You're gonna pick one out of the possibilities, or in this case, you're gonna roll the dice once. And then and would mean that one result has to meet it has to meet A, the criteria of A, and the criteria of B at the same time. So or then means as long as it meets the criteria of one of them, you're fine. So B or C would be 4 or more, and at most 2. So at most 2 would be 1 and 2, right? At most 2 would be 1 and 2, and then 4 or more, 4, 5, and 6. And it could be, this is or now, so as long as one of them is satisfied, we're good. So it's gonna be 1, 1, 2, 4, 5, 6. Did that help? Okay, good. Was it the fact that you didn't realize you were listing outcomes, or what was tricky for you?
I guess the and or.
Okay, yeah, and and then we're gonna, like I said, we're gonna work more on that today. But always for and or, you think about you're gonna do the experiment once, or you're gonna pick one from the population. And would mean that about that one that you're picking, everything has to be satisfied, or means about that one, any one of the conditions or the events could be satisfied. Question?
Can we look at number 6?
Okay, last one. Sure. Okay, so we're gonna toss the dime 3 times, and then there's the 8 possible outcomes when you do that. Okay, and so we want the probability that all 3 tosses come up tails. So we have an event here, and we're looking at how many of these satisfy that event. So how many?
1 out of 8.
1 out of 8. How many? Integer or simplified fraction. So 1. In this case, they don't want decimals. They want a fraction. Good on that one? Is that first one good? Okay. The last 2 come up heads. So again, we're going to go, that's our events. We're going to look at the 8 possibilities and ask how many of those 8 possibilities meet this criteria. So how many have the last 2 coming up heads? 2 of them, right? This one here, tails, heads, and heads, heads, have the last 2 heads. So 2 out of 8. But they want us to simplify it. So 2 out of 8 is the same as 1/4. Okay. All 3 tosses come up the same. How many possibilities? All heads or all tails? So there's 2 in this case, so 1 out of 4, or 1/4. the second toss comes up tails. So we just go through each one and see. So there's 1, there's 2, there's 3, there's 4. So the ones that the second toss is tails, yeah, it'd be 4 out of 8 or 1/2. That's right. So it's gonna be this one, this one, this one. All of these, the second toss is tails. So that's 4 of the 8, which is 1/2. Did it help?
Yeah, I totally overthought it.
Okay. Yeah, so it's just number of possible from the set divided by the total in the set, and then reduce your fraction. Okay. So let's talk about some kind of more about some of these issues with and or and sets. So what I want to do is I want to make some tables of data, and we'll just go ahead and some blank space here. So that's like too big. You want to see a cool thing I made for calculus? So there was a problem in calculus about driving from Phoenix to LA. And so I made this little animation for my students. So I made sure to get the car with a surfboard, because we're going surfing in LA. Okay. All right, so let's take a poll here. So we want to look at our class distribution here in our class. So how many are Ida High School? This is your first year in college. You are a freshman. 1, 2, 3, 4, 5. Beautiful. So event and frequency, right? And how many is your second year sophomores? 1, 2, 3, 4, 5, 6, 7. Awesome. And it's your third year after high school. You're a junior in college. 1, 2, 3. Any seniors? No seniors? Okay, and then we have non-traditional. Non-traditional. That's you?
Yeah.
Okay, I'm going to include everybody. 1, 2, 3. Is that everybody? So are there 18 people in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. What happened? 10? No, but I'm just counting the total of this and the people that are here. 4, 7, 10, 17, but I have...
I got counted twice.
Oh, for which one?
The junior and non-junior.
So you're not traditional, not junior?
Right.
Okay. Okay, now we got it. Okay. Okay, so what's the probability that someone is underclassmen? Again, we're picking one person. So how would you find the probability that someone is an underclassman? Meaning not a graduate student, not non-traditional. What would that be? What's that? So 12, where are you getting 12? Oh, so, okay, underclassmen, is that freshman and sophomore? Beautiful. Okay, that's great. I'm glad. Okay, so 12 over, for some reason I was thinking that was non-graduate students, so that's great. So underclassmen is freshman, sophomore, so 12 over 17. Let's get a decimal approximation. Okay, so how could we rephrase that event using and or? So how could we rephrase that event using and or? What would we say? Instead of underclassmen, we could say what for and or? Freshman or sophomore, or would it be freshman and sophomore?
Be freshman and sophomore.
Some are saying and, some are saying or. So remember, we're going to pick one person, and we want the probability that that person is an underclassman. So that one person, freshman and a sophomore, or freshman or a sophomore? Or. So this is the same thing as saying or. It all goes back to we're going to pick one person from the class, and we want them to be a freshman or a sophomore. Okay? And so how could wouldn't that be, so what is probability of a freshman? 5 over 17? Probability of a sophomore? 7 over 17? And do you see that I'm going to get the exact same thing if I do it this way. So how would I write that in symbols? That's probability of F plus probability of S. And I'm going to get the exact same thing. Okay, what is the probability of F and S? What's that? Why 0? Okay, so we're going to pick one person, and he's saying the probability is 0 because that person could not be a freshman and a sophomore. Agree? Agree. True. And so it's an impossible event. It's impossible for us to pick someone at random and for that person to be both a freshman and a sophomore, right? Those are, and so the reason, so that's impossible. And this is, we have a special name for this. Anybody know what this is? What kind of events these are? Mutually exclusive. Mutually exclusive events are two events that cannot happen at the same time. So it's impossible for it to happen. Two events, or two or more events, that cannot happen at the same time. Two or more events that cannot happen simultaneously. Okay, so let's try something else. How many people are Arizona natives? Arizona natives. Nice and high. 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many people are only childs? They don't have a brother or sister. 1, 2. How many people are wearing jewelry today? 1, 2, 3, 4, 5, 6. How many people like Mexican food? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I think we're good here. Okay. So, what's the probability so let's I'm going to name these events here. We'll call this event Z. We'll call this event S. We'll call this event J, and we'll call this event M. Z is you're a native Arizonan. S is you have no siblings. J is you're wearing jewelry today, and M is you like Mexican food. Okay, so what's the probability of Z or J? Probability of Z or J. So what are we doing? We're picking a person from the class, and they have to be from Arizona or be wearing jewelry today. And then they're those are the people we want. So let's just first of all, how many people so we can go that is in itself is an event. Z or J is a new event made up from the other events. How many people in that set for that event, Z or J?
So the formula would be rewritten.
No, let's ask this question. Just Z or J. How many people fit in this class of event Z or J, meaning an Arizona native or wearing jewelry today? 14. Agree with that? Everybody agree with that?
Yes.
Anybody from Arizona also wearing jewelry today? Raise your hand. No. So 2 people are wearing jewelry and from Arizona. When you made this tally of 14, what happened? What happened with them? No, they didn't get left out. So those 2, you raised your hand when I said Z, right? Arizona natives. And you raised my hand when I said you're wearing jewelry, right? So when we added 8 plus 6 to get the total of Z or J, what happened to those 2 people? They got counted twice. You see that? In the 8, they're included in the 8, and they also got included in the 6. So is this right? How many people fit Z or J? 12. It's not 14 because it's going to be the 8 from Arizona plus the 6, but anyone who was both got counted twice. So what would we do? We would subtract them out to get the right total. Does it make sense?
Yeah, but how do you know how many people were included?
Because I asked.
Huh?
I asked.
You asked?
I asked. I said. But the point is that it's not going to be 8 plus 6 because there's at least one who is both. Right? So if we knew there were none that there were both, then we were okay. But so it's this probability of picking someone that's from Arizona or wearing jewelry should not be 14 out of 17, but instead should be 12 out of 17. Because if I said, okay, raise your hand if you're from Arizona or you're wearing jewelry today. Raise your hand. Everyone raise your hand if you're in the Z set or the J set. Raise your hand. How many should I get? 1, 2, 3, 4, 5, 6, 7, 8. What happened? Is there more people that are both? Okay, raise your hand if you're a native Arizonan. 1, 2, 3, 4, 5, 6, 7, 8. That's not a hand, right?
No.
Raise your hand if you're wearing jewelry today. 1, 2, 3, 4, 5, 6. Raise your hand if you're in native Arizona or you're wearing jewelry. So there should be 12 of you. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's going on? Who's? You guys aren't following instructions. The math works, but our brains have to work too. If you're a native Arizonan, raise your hand one more time. 1, 2, 3, 4, 5, 6, 7. There's 8. Good. If you're wearing jewelry today, raise your hand. 1, 2, 3, 4, 5, 6. Okay. If you just raise your hand one of those 2 times, raise your hand again. How many people should there be? 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're getting closer. Did I forget to count her? Okay, raise your hand high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Still getting 11.
Maybe somebody didn't raise their hand for.
Yeah, someone's not raising correctly.
They're from Arizona and
I just got confused.
Are you from Arizona or wearing jewelry?
Yeah.
Yeah, then why aren't you raising your hand?
I don't know, that last one confused me.
Are you from Arizona or wearing jewelry? So,
Yeah.
not and, or. You're from Arizona or you're wearing jewelry. Is that one of those things true?
Yeah.
Yes. Then raise your hand. Okay. So that's 12. Okay. So it's not 14. It's not 8 plus 6. Sorry. It'd be a lot more effective if it worked. But anyway, so if we wanted to do it by the individual probabilities, probability of z, could we do probability of z plus probability of j? No, that'd be too high because it has the same effect. It would be overcounting. But if we took that total, we could do what to it to make it right? Subtract. What event would we be subtracting? Z and j, right? Z and j. We've already counted z and j. We counted z and j here. We counted z and j there, so they got counted twice. So if we subtract it out once, it makes the total right. Okay, or, so it'd be 8/17 plus the 6/17 minus 2/17 gets us the right probability for P or Z or J. Question?
How are these problems going to be set up on the homework? Like, how are we going to know which people that, or which...
You'll have all the data in front of you. So you'll have all the data.
So we'll know if...
Yeah, you'll have enough
somebody's
information.
more than one.
Yeah. Yep. So whatever problem they throw at you, somehow you'll have all the information you need. There's different ways they could phrase the problem, or they could come at it from different directions. But you'll always have all the information you need to make the conclusion. Why is the denominator 17? What's that? Okay, so they want to add up the frequencies. You want to add these up, and what'd you get? Does it make sense? Why not? Yeah, so it's the same issue as before. So when you have when you have the Arizona people and the jewelry people, that just overcounted twice. And then what about the Mexican food? So we have. So this is a great point, because this is not a good way to organize this data, because it kind of so this is not ideal, because we can't do this and sum up and get all the members in our set, because we've double counted all over the place. We double counted when we got to jewelry, maybe siblings. We definitely double counted when we counted everyone in Mexican food. Does it make sense? So what is it about what is it about this data here for this table that's different than the data in the first table? What's that? Right. So the table way of organizing data is convenient when your events are mutually exclusive. You see? This is not really the best way to organize this data in a table, because we have non-mutually exclusive events. Okay?
So they'll like that, and I don't know, mark it on the list how many people are in the class or whatever.
Yeah, so you won't see this. Okay, so I'm making this is kind of a negative example. You'll never see a table like this of non-mutually exclusive events. Okay, so so what happened with the math? When you have mutually exclusive events, how did we calculate the probability of OR? With mutually exclusive events, how did we calculate the probability of OR? You just add them. It's easy, right?
Yes.
This is called the special addition rule. Special because you have special events. They're mutually exclusive. And so you can just add the probabilities. It's really easy. When you don't have mutually exclusive events, it's just called the addition rule, where you have to subtract out the probability of the AND case to adjust for the overcounting that you did. You see? We overcounted by 2 when we did that. And so you have to subtract those 2 people out one time to compensate so that we truly get the 12 out of the 17 who were the OR. So this is just called just the addition rule. So the addition rule, they're both about the probability of one event or another happening. When you have mutually exclusive events, you can just add the probabilities because the probability of them both occurring is 0. So you don't have to subtract this because it's 0 already. But if you have non-mutually exclusive events, you have to account for that double counting and subtract off. That's just the plain addition rule. Okay, does that make sense? So let's look at a better way rather than this way. So a table, when you have non-mutually exclusive events, a table is not a good way to organize that data. So we have another thing called a Venn diagram. That's a better way when you have non-mutually exclusive events. So can I erase what I've written so far here? We good? Okay, so let's go back to that same set of data. So we had Z was Arizona natives. What was that? 8. And then S for no siblings was 2. And then J for wearing jewelry was 6. And then M for Mexican food was 13. Okay. So let's look at, this time let's look at these 2 events. Arizona natives. And what we're going to do is we're going to make what's called a Venn diagram, which is a visual way to represent this. So we're going to make a circle that represents the Arizona natives, okay? And so if you're inside the circle, you're an Arizona native. If you're outside the circle, you're not an Arizona native. So we're going to make that circle. And that's our Z circle for Arizona natives. Okay, and then we have people who like Mexican food. So what will the total of people be in the Z circle? 8. All right, and then the total in the M circle will be 13. But are those mutually exclusive events?
No.
Okay, we can be almost sure that they're not, right? In fact, we know that they're not because 8 plus 13 is greater than 17, right? 8 plus 13 is 21. There's only 17 people, 17 of you guys, those absolutely have to be not mutually exclusive. Okay? There's no way they could be mutually exclusive because when you total them up, you get more people that are in the class. So what does that mean? It means there's some people that are just Arizona natives, some people that are just Mexican food lovers, and some that are both. And so by making overlapping circles, we account for all the different possibilities. So how many people were Z and M? You raised your hand when I said Arizona native. You also raised your hand when I asked that you like Mexican food. How many is that? 1, 2, 3, 4, 5, 6 of you. Did you just raise at the end?
Is that Mexican food?
No, both. Both. You raised your hand
Oh, never mind.
when I said you were Arizona native, and you also raised your hand when I said you like Mexican food. Nice and high. 1, 2, 3, 4, 5, 6, 7. Okay? So that we're going to put this here. 7 of you were both because 7 of you are Arizona natives, so you're in the Arizona circle, but you also like Mexican food, so you're in the Mexican food circle. So then, by deduction, we can just deduce how many Arizona natives do not like Mexican food. 1. How did you know that? Yeah, because there's 8. There needs to be 8 total in the Arizona circle. That means there was 1 Arizona native. So who was that? Who was an Arizona native who said that you didn't raise your hand for Mexican food? There should be one of you. Is that you? Okay, good. Okay, good. All right. So then, what about people who love Mexican food but are not from Arizona? How many? So first of all, before we raise hands, how many?
6.
Should be 6, right? Because the total in the Mexican is going to be 13. 6 do not. 6 are not from Arizona. Okay? So now, in addition, now we can also find out how many people were neither of these. So how many people are neither Arizona natives nor they like Mexican food? So how many? Can you figure it out from the numbers? Not raising hands. And how do you get 3? Yeah, so we've counted for 14. If there's 17 total people in the class, that means there's 3 not accounted for. So we can put them outside both circles. So this is a much better way to organize the data rather than a table when you have non-mutually exclusive events. But if you do have mutually exclusive events, or so this is called the counting Venn diagram. Why? Because it's just counting the number in each the number for each event. That's the counting Venn diagram. But then we could also make a probability Venn diagram. And so instead of just how many people, it would be the probability. You'd have the exact same, it would look exactly the same, but then you'd have probabilities instead. Okay? So this is not going to be, is this going to be the probability of from Arizona right here? Right. It's both from Arizona and not liking Mexican food. And how what would that probability be? Just as a fraction is fine. 1/17. This in here will be the probability of both, or the and situation. A person who's from Arizona and likes Mexican food. 7/17. So what would this situation be?
6 over 17.
But what situation would it be? Likes Mexican food, but not from Arizona. And finally, not from Arizona, don't like Mexican food. So the probability of Z or M, now we have actually 2 ways to think about it. 2 ways we have the addition rule. The addition rule says that it should be the probability of Z plus the probability of M. Then what? Z and M. Okay, so probability. So what is probability of Z? What is probability of Z? 1/17? 8/17, right? So go back to, we have 8 people from Arizona, or you'd have to sum up the 1 plus 7. Everyone in the Arizona circle. So it'd be 8/17 plus 13/17 minus the overlap. So we want to. So if we've double counted how many people when we included them in Arizona and we included them in Mexican, how many people got double counted? 7. So they're counted twice. So we want to subtract them out once, so that they'll be only counted once, right? So if they're counted twice, we can just subtract them out once, and now they'll be counted just once. 14/17. Okay, but now now you can do this a different way, looking at your probability Venn diagram, or looking just at your counting Venn diagram. So that's the idea of the addition rule. Addition rule. You're adding the individual probabilities, subtracting out the overlap. But with the diagram, if we want the probability of Z or M, which of the people fall in that category, Z or M? How many? Do you see? It's just, you can just add straight across. 1 plus 7 plus 6. Because there's in the diagram, there's no overlap. You've broken it down all the way. 1 who's just Arizona native, 7 that are both, 6 that just like Mexican food. So using the diagram, we can just do 1 plus 7 plus 6 over 17, which is the exact same thing as using the addition rule. Do you see it? They're both 14 over 17. Because Z or M will be anybody in either of the circles. And you just do 1 plus 7 plus 6. So this is using your chart. This is addition rule. Both give you the same result, 14 over 17. Anybody have a question? Yes, please.
Given this data, how would you know the number of people that didn't like Mexican food but were Arizona?
Yeah, so this is not all the information that we had to make this diagram, right? I had to ask you another question.
Yeah.
I had to ask you the and question. I had to say, how many are Arizona and? So if in order to build this diagram, you needed more than just the 8 and the 13. You couldn't have done it. If you just had 8 and then 13, you knew that total had to be 8 and that total had to be 13, but you didn't have enough information to do this. So I asked the additional question, how many are both? And that allowed us to finish the diagram. Yeah, good question. Anybody else? Any questions? Okay, and so then what about the not situation? So we can go back to looking at not. So looking at this diagram, so what's the probability that a person does not like Mexican food? Who is included in the people that do not like Mexican food? How many?
4.
They say 4. Agree? So just outside the Mexican food circle. So this person doesn't like Mexican food, and these 3 people don't like Mexican food. So the probability would be 4 out of 17. Okay? What's the probability of not Mexican food and Arizona native? So the probability that someone does not like Mexican food and is not an Arizona native. So not Z and M. So not both. How would you do that? How many? 10 people. So this person is not Z and M. So those 6 and so those 3. You see? So not Z and M. So Z and M is the 7. So everyone else would be the 10. That'd be 10 out of 17. And then what about not Z or M? How many? 3. Z or M is somewhere in this region here. So that'd be the 3 out of 17. So everything I'm shading is representative of Z or M. Z or M, which we know is 14. 14 or 14/17 probability of picking someone would be 14/17. Okay. So let's just, there's just a couple slides, just kind of just review the definitions, review the things, the new things here. Can I erase the screen? Okay, so here's what we talked about with these Venn diagrams. So first not would be everything, so the shaded is what, so if E is inside the circle, then not E is everything outside the circle. The and situation is you're picking one, remember you're picking one thing, or you're doing the experiment one time, and both events have to be satisfied. And that would be the overlap of the 2 circles. And then A or B could be anywhere in either the A or the B circle. So it'd be the shading of the figure 8. Okay, so these 3 things we're talking about. Not, and then or. Not, and or. Questions about any of those? Okay, next slide. So this is just the language, not E, the event E does not occur. A and B, both A and B occur. And A or B, either A or B or both occur. Okay, mutually exclusive. 2 or more events are mutually exclusive if they have no outcomes in common, right? We said that, no outcomes in common. And so here's what the pictures would look like. Mutually exclusive, you would draw it like this, because there's no overlap. If you're in A, you can't be in B. If you're in B, you can't be in A. But if they're not mutually exclusive, you could be in both. You could be in both. All right, so this is for 3 sets. We won't have any problems like that, but mutually exclusive, again, would mean there's no, if you're in A, you can't be in any of the others. If you're in B, you can't be in any of the others. Mutually exclusive. Okay, so if mutually exclusive, when you're doing the OR situation, we saw that if they're mutually exclusive, you can use this thing called this is the special addition rule. You can just add the individual probabilities because there's no overlap to worry about, right? There's no overlap to worry about. Okay, look, we didn't mention this today. We mentioned this last time, but the complementation rule is for not. So if you have a probability and you want the probability of not that, it's going to be everything else, and so it'd be 1 minus that probability. Because in probability, the total of everything has to be 1, right? So if you add up all the possibilities and the probabilities of all possibilities, that will have to be 1. So not is going to be 1 minus. And then our general addition rule is for any 2 events. Takes into account if you have overlap. Like they're not mutually exclusive. You have to subtract that out for the double to get rid of the double counting. Okay, so I think that settles it. So we'll do the same thing for next Monday. You'll have the online homework and then a take-home quiz. Okay. So you can email me, or I got office hours tomorrow morning. If you need help outside of class, don't hesitate to get help from me. And you can email me questions too if you've got questions. I think there's an Ask Your Instructor button on the right on the online homework. You can use that if you want. Send me a message, okay?